So with related rates, up to this point, you've seen how the chain rule could be used to find like dy dx implicitly. Well, another important use of the chain rule is to find rates of change of two or more related variables that are changing with respect to time. And that's what's referred to as a related rates problem. But let's go ahead and first practice taking a derivative implicitly with respect to t. Okay, so for example, let's take this volume v equals 2x squared minus 6y. Okay, and let's go ahead and take the derivative this time instead of d dx. Let's go ahead and take it and practice taking it with respect to t, because we'll be later taking these applied problems with respect to time. So let's take this derivative with respect to t. So what we would have is 1, derivative of v is just a 1, dv dt, right, v prime, equals, these variables also do not agree, right? It's taking the derivative with respect to time, so 2x squared, well, that's different than t. So it's just 4x dx dt minus derivative 6y is 6 dy dt. And then it says, well, find dv dt. So here's our 1 dv dt. So find dv dt when x is 3 given dx dt and dy dt. So x is 3, dx dt they give us as -1, minus 6, dy dt they give us as 4. So it looks like this dv dt just ends up being -12 minus 24, so -36. Let's do one more like that. Let's take the derivative with respect to time, or with respect to t. So x squared plus y cubed equals 15. And let's go ahead and take that derivative with respect to t. So you've got 2x, again, variables do not agree, so dx dt plus 3y squared, variables do not agree, so dy dt, chain rule, equals derivative of constant, of course, is 0. It says find dy dt, so find that when x is 3, y is 4, we don't know dy dt, and dx dt over here, dx dt is 8, looks like. So they gave us everything except dy dt. So we got 6 times 8, we got 48, plus 3 times 16, I got 48. dy dt equals 0. I'm going to subtract 48 on both sides. So I got 48 dy dt equals -48. I'm going to divide by 48. So -48 over 48 is just a -1. So it looks like dy dt with those givens is -1, and that's how you take the derivative with respect to t. Well, let's get into the applications here. So this time we've got a point. It's moving along the graph of y equals 1 plus x squared. If you're graphing that, it looks something like this kind of deal. Right, there's your 1 plus x squared. So a point's moving in the x direction 2 centimeters per second. How fast? All right, so it's just we just got some point moving along this axis, right? It's like moving. Let's say it's along this graph, right? And they give us that it's moving in the x direction is 2 centimeters per second. Okay, and so that's their rate of change. Let me go ahead and points movement in the x direction. They are giving us the rate of change at a certain time. They're giving us that it's moving 2 centimeters per second, right? They're giving us how fast it's moving. So, and they ask, how fast is the point moving in the y direction? So what's dy? So how about in the y direction vertically? How fast is it moving when at this exact moment x is -2? When x is -2, How fast is the point moving in the y direction? So the rate of change with respect to time, dy dt, is what they're asking for, right? What's dy dt when x is -2? Okay. So like if I'm looking at this visually, like if this is -2, I'm moving 2 centimeters per second in the horizontal direction. What am I moving in the vertical direction right at that moment, right? When x is -2. That's kind of what it's saying here. Well, what do we have? We have this equation, y equals 1 over 1 plus x squared. Let me write that as just 1 plus x squared to the -1. And I'm trying to find the rate of change in the vertical direction with respect to time. So I got to take d dt. That's why we practice taking the derivative with respect to t. Let's go ahead and take d dt on both sides here. And so we'd have 1 dy dt equals, now I'm taking the derivative with respect to t over here. Power rule, -1, 1 plus x squared. Now it's to the -2. Derivative of the inside is just 2x. Don't forget dx dt. Whoops, that's a dt right there. dt. Let's see if I can fix that. There we go. So dy dt is -2x over 1 plus x squared dx dt. Now, what are we given? Well, we were given dx dt, so this is 2 centimeters per second. Let's substitute this in. At the moment, x is -2. So we got to replace x with -2 as well. So let's make the substitution. So what's the rate of change in the vertical direction, dy dt, when x is -2? And dx dt is 2 centimeters per second. So it looks like dy dt ends up being 4 times 2. I've got 8 over 1 plus -2 squared is a 4, but that's squared. So dy dt looks like 8 over 25. This would also be centimeters per second, right? If your position's in centimeters, your change in the vertical direction is centimeters per second, right? So in other words, the point's moving vertically 8/25 centimeter per second at that moment when x is -2 and when the x direction movement is 2 centimeters per second, right? It's moving 8/25 in the vertical direction. Let's do another one. A stone is dropped in a puddle causing a ripple, right? So a stone's dropped and it's getting these ripples, right? It's going bigger and bigger ripples. I didn't draw those very good circles. So the radius r of the outer ripple is increasing, right? So if you can imagine, let me erase the inside of these. Here's our radius of this thing. So the radius r is increasing at, in other words, its rate of change is changing, right? Because we have these concentric circles, right? As time goes on, that radius is getting bigger, 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 right? So dr dt, 2 centimeters per second. So per second, the radius is increasing 2 centimeters per second. Does that make sense? That's our dr dt. When the radius is 0.5 meters, at what rate is the total area changing with respect to time? So what's dA dt? How much is the area changing over time, right? How much is the area changing? Well, hopefully you notice these units aren't agreeing. I have a radius of 0.5 meters and a dr dt of 2 centimeters per second. We need this. So let's change that 0.5 meters. We know there's 100 centimeters per meter, right? So let's get this radius. 0.5 times 100 is 50 centimeters. That's the useful one, right? We're going to stay in centimeters here. So we've got radius 50 centimeters. At that moment that the radius is 50 centimeters, 50 centimeters. At that moment, we know dr/dt is changing at 2 centimeters per second, but what's the area changing at that moment? Right at that moment, right? If we take a snapshot in time. Well, we know area of a circle pi r squared. So let's go ahead and take the derivative with respect to time. d dt. And we'll have 1 dA dt equals 2 pi r dr dt. So dA dt equals 2 pi. It's at the moment that our radius is 50 centimeters and our radius is changing at 2 centimeters per second. So our dA dt would be 2 times 50 times 2. Looks like I got 200 pi centimeters times centimeters, square centimeters per second. That's how fast the area is changing. It's increasing 200 pi square centimeters per second. All right, let's take a look at this one here. We've got a volume of a sphere. So here's a volume of a sphere. If you can imagine a sphere, I can't draw worth beans, but I'm going to give it a shot here. With the radius, right? Here's our radius of that thing. The radius is changing at a rate of changing, right? So they're giving us, like this thing is like being blown up, 2 dr dt. The radius is changing at 2 inches per minute. Okay. What's the rate? How fast is the volume changing? So what's dv dt would be what? At the exact moment that the radius is 6 inches, right? So imagine again you're like blowing this balloon up or whatever, right? And you're blowing it up. The radius is changing at 2 inches per minute, right? So how fast is the whole volume changing at the moment that the radius is 6 inches? Well, we know our volume is 4/3 pi r cubed. So if we take this derivative with respect to time on both sides, and we have dv dt equals 4/3 pi stays there, 3r squared dr dt. Notice the 3's cancel. So our dv dt would be 4 pi r squared dr dt. Now let's fill in what we know here. We're looking for dv dt. We don't know that. Our radius is 6 inches, so the 6 inches is squared. Our dr dt is 2 inches per minute. And so our dv dt ends up being 4 pi times 36, 288 pi cubic inches per minute, right? Cubic volume, remember volume's in cubic units, right? So cubic inches per minute. That's how fast that thing's getting blown up or whatever. If you can imagine maybe a balloon, perfect spherical balloon getting blown up. All right, this next one, we got a conveyor belt dropping sand. So if you can imagine this, it's got this conveyor belt with sand that's dropping the sand into like this conical pile. I can't draw worth beans, but I'm trying to give this a shot here. Here's our height. Here's our radius of that thing. And notice they tell us the radius is always twice the height. Radius is always twice the height. Sand is falling at a rate of, so there's a rate of change. Sand is falling. Sand is a volume, right? Sand has volume. So they're telling us dv dt is 5 cubic meters per second. How fast is its height increasing? How fast is its height increasing at the moment, right when the radius is 20 meters? So the volume's changing 5 cubic meters per second. But how fast is its height? dH dt. at the moment that the r is 20 meters, right? Well, let's go ahead and take our volume of a cone. So 1/3 pi r squared h. And we're going to go ahead and put this, the fact that I know that the r is 2h, I'm going to go ahead and substitute that in. So I'm only dealing with h's here. And so I don't have to do like the product rule and make a big old mess of this, right? So that's a key bit of information here. So I got 1/3 pi 2h is being squared times h. So I got 4/3 pi h cubed. Now let's take this derivative with respect to time. This will be much cleaner. So dv dt would be 4/3 pi, 4/3 pi is our constant, then 3h squared dh dt. Notice the 3's cancel. So dv dt ends up being 4 pi h squared dh dt. Let me write that, dh dt. Now, we're trying to find it at the moment when the radius is 20 meters, right? Well, if the radius, remember r is 2, if r is 2h, and if our radius is 20 meters, then our height would be 10 meters, right? So let's plug that in for our h right there. And we're trying to find our dh dt. dv dt is also given. There's our dv dt, 5 cubic meters per second. So I got dv dt is 5 cubic meters per second equals 4 pi, our h is 10 meters squared, and we're solving for that dh dt. So we have 5 equals 4 times 100. I got 400 pi dh dt. So dh dt is 5/400 pi. So dh dt is 1/80 pi. And this is in meters per second, by the way, if you kept your units there. That's how fast the height is changing again at that moment. All right, the length L of a rectangle is decreasing at the rate of 2 centimeters per second. So if you can imagine for a minute, you've got this rectangle, here's my length, here's my width. The length is decreasing. So they're given dl dt, decreasing, make it negative, -2 centimeters per second because it's decreasing, right? dl dt is decreasing negative. Now the width is increasing. So this, on the other hand, if you can imagine this, the L's going in, the W's going out, okay? So the dw dt is positive. It's increasing at the same rate, but increasing, right? Increasing. Now when L is 12 centimeters and W equals 5 centimeters, find the rate of change. So find the derivative, rate of change. Find the rate of change of the area. So we want dA dt. So part A, we want dA dt. And then we'll talk about the perimeter, dP dt. And then we'll finally address the lengths of the diagonals. Okay. Well, area is length times width. Let's take the derivative with respect to time. So we've got dA dt equals derivative of the first times the second plus the first derivative of the second. Now I got to plug my stuff in. So I got dl dt was negative 2 centimeters per second. My width was 5 centimeters. My L was 12 centimeters. The width is changing, increasing at 2 centimeters per second. So I've got negative 10 square centimeters per second plus 24 square centimeters per second. So my dA dt, the area is changing or increasing at that exact moment 14 square centimeters per second. Okay. So if you remember, perimeter is adding up all the sides, L plus W plus W, so 2L plus 2W. And we want to know how fast is that changing? Well, dP dt would be 2 dL dt plus 2 dW dt. And so then you just plug those in. So dP dt, the perimeter is changing. The L is negative 2 centimeters per second. The dW is positive 2 centimeters per second. So it looks like I got negative 4 centimeters per second plus 4 centimeters per second, which is 0 centimeters per second. Which makes sense because the length is reducing at a rate of change of -2. The width is increasing. So perimeter is not changing, right? In other words, the perimeter is constant at this moment. All right, the last part of this says, what about the lengths of the diagonals? Well, the rate of change of the length. So let's go ahead and draw the length here of the diagonal. Let me call it capital D for length there. Well, we know from the Pythagorean theorem, we would have D squared equals L squared plus W squared. And so what's the rate of change that that diagonal, capital D, is changing? Well, let's check the derivative with respect to time. So I'd have 2D capital D dt equals 2L dL dt plus 2W dW dt. And let's start filling in. Now, what is my diagonal? At the moment, length, if my length is 12 centimeters, my width is 5 centimeters, I would want to solve for my diagonal with the Pythagorean theorem, right? So I'd go to the side and I'd go ahead and solve that. D squared equals 12 squared plus 5 squared. So D ends up being 13 centimeters. That's that diagonal right here, 13. So now we can plug that in right here, right? 13. So we got 2, we got a 13. We're solving that, how fast that diagonal is changing, dd dt. Our L was, what was it, 12? It's changing though, it's reducing, decreasing at 2 centimeters per second. The width at the moment that it was 5 centimeters, and it was changing, increasing at 2 centimeters per second. So we got 26 dt equals negative 48 plus 20. So negative 24. Oh, I'm sorry, negative 28 over 26. Centimeters per second. That's how fast. So the diagonal is decreasing. The length of that diagonal is decreasing at 13 centimeters per second at that exact moment, right? When with that fixed length and width. All right, we've got this 13-foot ladder. Notice it's marked there, the length of the ladder. So think right triangle trig, right? We've got this right triangle here. And it starts to slide away from the base, as shown there. by the time the base is 12 feet from the house, right, here's my x, here's my y. So at the moment, so when x is 12, when it's 12 feet from the house, right, from here to here, the base is moving, dx dt is 5 feet per second. Okay. Find the rate at which the ladder is falling down the side of the house. dy dt would be equal to what? Well, we know we have x squared plus y squared equals the 13-foot ladder squared, right? And we know that x is 12. So 144 plus y squared equals 169. So it looks like y ends up being 5. Right? So that'll be useful for us. Y is also 5 feet when x is 12. Y is 5. Okay. So what do we have? Well, we have this x squared plus y squared equals 13 squared. And we're going to take this derivative with respect to time. So we've got 2x dx dt plus 2y dy dt equals derivative of 169, 0. Our x is 12. Our dx dt is 5. Our y is 5. We're solving for dy dt. That's that rate at which the ladder's falling down, right? It's going down. How fast is it going down? That's the question, right? That's the dy dt that we want. So 120 plus 10 dy dt equals 0. 10 dy dt equals negative 120. So dy dt divided by 10 is negative 12. This is in feet per second. So the ladder, again, right here, that ladder's going down, right? It's changing 12 feet per second on that. Okay? 12 feet per second. All right, that's part, let's see what they call it. Part A, that's part A. Let's do part B now. Part B says, consider the triangle formed by the ladder, the house, and the ground. Find the rate at which the area of the triangle is changing. Well, if you remember, area is 1/2 base times height. So in this case, area is 1/2 base times the height y. So I'm going to think about this. I'm going to do this as a product when I take this derivative with respect to t. So I'll have dA dt, derivative of the first, 1/2. Don't forget dx dt, derivative of the first times the second plus the first, derivative of the second. Well, the derivative of y is just a 1 dy dt. And we're trying to find this dA dt. So we got 1/2. Our dx dt, what was our dx dt? 5. Our y was 5. Our x was 12. And our dy dt we found was negative 12. And so it looks like we have 25 over 2 minus 144 over 2. And so this is in square feet per second, by the way. This is feet per second. This is in feet per second. So this is square feet per second. Let's see, that'd be negative 119 square feet per second. So the area is decreasing 119 square feet per second. Part C. At what rate is the angle theta? Okay, so we've got this angle theta right there. How about at what rate is it changing? So d theta dt when the base of the ladder, again, is 12 feet from the base of the height. Well, you want to use one of your trig, right triangle trig. one of your trig functions, I would probably just use the sine of theta here. You remember the sine of theta is opposite, so the opposite would be the y over hypotenuse of 13. And then I just take that derivative. Derivative sine, cosine theta, d theta dt. That's what we're looking for. Now think of that as 1/13 y. So it's just when I take the derivative, it's 1/13 dy dt. And then I'd say, well, what's my cosine of theta? So note that the cosine of theta is adjacent 12 over hypotenuse 13. 12 over 13. Okay. And so I could go ahead and fill that in. Cosine of theta, 12 over 13, d theta dt equals 1/13. And then dy dt is negative 12. So d theta dt ends up being negative 1. This is radians per second. All right, let's keep going here. This time we've got a police cruiser, and it's approaching a right-angled intersection. Let me have this police cruiser. Let's have the police right here. There's a police cruiser. It's approaching this right-angled intersection from the north, right? And it's chasing a speeding car. It's already turned the corner. Is moving straight east. Here's the chase car. Right, it's moving that way. Now, when the cruiser is 0.6, let's have this be y, 0.6 miles north of the intersection. The car is 0.8 miles to the east. The police determine that the radar, that the distance between them and the intersection, between them and the car is increasing. Let's call this S right here. So ds dt, this straight distance between them is changing 20 miles per hour. Okay. So we're given x is 0.8 miles, y is 0.6 miles, and the distance between them is changing at 20 miles per hour as they both move. Okay. So what do we have? Well, Pythagorean theorem, x squared plus y squared equals s squared. I'm going to take the derivative with respect to time. Left to all right, so we got 2x dx dt plus 2y dy dt equals 2s ds dt. So our x is 0.8, our dx dt plus 2y 0.8 and I should have said if the cruiser is missing, I forgot one more given here, my apologies, right here. If the cruiser is moving at 60 miles per hour, so that's our dy dt. And notice it's going in the southerly direction. So getting closer to the origin, so minus 60 miles per hour. So that'll go in right here for dy dt, minus 60 miles per hour. Our s, we need to find our s as well, but our ds dt was given as 20 miles per hour. Notice our x squared plus y squared equals s squared. So if x is 0.8, our y is 0.6, square root that. I get 1 on that, so that would go in. 1 would go right there for the s. I made a mess of this thing. But I got 1.6 dx dt. That'd be minus 72 equals 40. I add 72 to both sides. I got 112, and then I divide by 1.6, so I got 70 miles per hour. And so that 70 miles per hour, that's how fast that chase car is going. All right, this one we've got a hot air balloon is rising straight up from a level field. Let's draw this. Here's our level field. We got this hot air balloon rising up. All right, here's our hot air balloon that I can't draw worth beans. But anyways, it's rising straight up from the level ground, but it's being tracked by this rangefinder. Here's the rangefinder over here, which is 500 feet from the liftoff point, right? That liftoff point right there, close to the right triangle, right? Goes straight up this balloon. At the moment, the rangefinder's elevation is pi force, so this theta angle is pi force. The angle is increasing, so we're given, let's see what we're given here. Let's write all this down. We're 500 feet from the liftoff point. The angle of elevation is pi force, and at the moment the rangefinder's elevation is pi force, the angle's increasing. So d theta dt, the angle is increasing at 0.14 radians per minute. How fast is the balloon rising? Let's call this y. So how fast is that rising? dy dt would be what? All right, this balloon's going up, so what's dy dt is the question, right? Well, I'm going to go ahead and use tangent because I know the tangent of theta is opposite over adjacent. Now I've got that 500. And I'm trying to find dy dt, so I want to involve y as well. So if I multiply both sides by 500, I'd have 500 tangent theta. And then I just got to take the derivative with respect to time here for this related rate problem. And so I get dy dt equals 500 stays there, derivative of the tangent secant squared theta. Don't forget chain rule d theta dt. So my dy dt equals 500. Now my theta, this is the secant of pi force squared. And my d theta dt was given. It was 0.14, right? Well, the secant of pi force would be, instead of 1 over root 2, be root 2 over 1. So it'd be root 2. If I'm looking at my unit circle, it'd be the reciprocal of the cosine there, right? Again, if I'm looking at my unit circle at pi force, oops, it's root 2 over 2 is the cosine. Well, I flip that over, it'd be 2 over root 2. And then I rationalize that. And so I have 2 root 2 over 2, which is root 2, and that would be the secant of pi force. So I got 500, secant of pi force is root 2, it is squared, times 0.14. So I got 500 times 2 times 0.14, which is 140. and this is in feet per minute here. And that's how fast the balloon is rising, right? 140 feet per minute. That's how fast that balloon is rising at that moment. All right, we got a man here that is walking. Let's draw this towards a street lamp. Let's draw our street lamp. Here's our street lamp. Not a very good street lamp. I cannot draw. Got this man that's 6 feet tall, walking at a rate of 3 feet per second. So let's go ahead and say, let's label a few things here. Here's my street lamp. That's 15 feet above the ground. Here's my street lamp. Here's the tip of the shadow, right? And so let's go from street lamp to the tip of the shadow. Let's call that X. And let's call the distance Y from the man to the street lamp. So here's my Y from the man to the street lamp. And so what are we given? The man, who's 6 feet tall, is walking at a rate of, so the rate of change is 3 feet per second towards the street lamp, right? He's moving this way, so that dy dt is changing at 3 feet per second, okay? At what rate is the tip of the shadow moving? So in other words, what's dx dt? Dx dt would be what? Well, what you want to do is you want to use similar triangles here. All right, you've got this. Here's the man and his triangle. Here's the big one with the street lamp. If you notice, this distance would be x minus y right here. The x minus y for right here. Okay, so what I'm going to do is I'm going to go 15 is to x, 6, I'm sorry. 15 is to 6 as x is to x minus y. 15 is to 6 as x is to x minus y. And so if I cross multiply that, I have 15x minus y equals 6x. So 15x minus 15y equals 6x. Let me subtract 6x on both sides. So I have 9x. Let me add 15y to both sides equals 15y. Okay, here we go. 9x equals 15y. I can take this derivative with respect to time now. And I'll have 9 dx dt equals 15 dy dt. And I don't know the dx dt. We're trying to figure that out. The dy dt, the man was walking towards the street lamp at 3 feet per second. So dx dt would be 45 divided by 9, so 5 feet per second. That's the tip of the shadow. The length of the shadow is decreasing, right? I'm sorry, the rate of the tip of his shadow is moving at 5 feet per second, right, as he walks. That's the rate at which the tip of the shadow moves. All right, part B here. What about the length of his shadow when he is 40 feet from the base of the light? Well, if this x minus y, or I'll call it s, right? The s is the distance x minus y, or s, right? Well, that would be the length of the shadow. So at what rate is the length of the shadow decreasing? Not the tip of the shadow moving, but the length of the shadow. How is it decreasing? Well, we know So this would be part B, I guess we called it. We know the length is x minus y. So let's go ahead and take that derivative with respect to t. And we've got ds dt equals 1 dx dt minus 1 dy dt. And we know the dx dt is the 5 feet per second minus the dy dt was 3 feet per second. So the length of the shadow is changing 2 feet per second. Note here, in both of these cases, as long as the man is moving at a constant rate, the rate of his shadow will also remain constant, regardless of how far away he is from it, right? Because this one is saying when he's 40 feet from it. Well, it doesn't matter. It's still changing at 2 feet per second because he's moving at a constant rate. Notice there's no extra y there involved right after we've taken that derivative. Right? Well, thanks so much for watching. I hope that helps. See you next time.